So in order to introduce to you the topic of today, I have prepared the following agenda. And before we start with the content chapters, we will have a quick look at the context, and I will also in the context introduce to you the structure, respectively the agenda in greater detail. So let us start with the context of my research. So the overarching research question that I would like to shed light on is, do artificial intelligence systems understand concepts? And with the phrase of understanding, I'm well aware of that this is not a technical term, and in the end it should be replaced actually with a technical term, which could be, for example, how could concepts be represented in AI systems, or how they are embedded there, or how they are processed there. But I want to express with this general notion of understanding that I'm interested in just this general intuition of how understanding of concepts works in AI systems. And this overarching research question in the end breaks down into a 3 years project that is planned to investigate it a little bit in detail. And what we are focusing on today is the very first year of my research, which is going to be specifically about the literature review on the concepts lifecycle in AI systems. So all the contents in the following will focus on this literature review, which hopefully is going to be result in a paper that I'm going to publish after the first year. So what is this literature review about, and why am I doing it? And what I do want to achieve with this literature review is I would like to understand how modern AI's concept processing capabilities differ from humans. And why am I doing this? I do think that this sort of research profits both the HI and the AI sciences. And when I'm talking about HI sciences, I refer to the human intelligence sciences, meaning all the sciences that examine human intelligence systems, such as psychology, linguistics, or neuroscience. And I do think, or as of now, I have not found any literature that systematically examines the interfaces of AI and concepts. And with systematically, I mean conducting a systematic literature review that holistically, or rather holistically, has a look at the literature on concept processing capabilities. So that's the what and the why. Let's have a quick look at the how I would like to achieve this. I would like to achieve this in 3 steps, of which the very first one is about the understanding what AI systems are, what are concepts, and what are concept processing capabilities. So in the beginning, for sure, I want to lay out the theoretical fundament, and on the basis of that, I would like to derive the taxonomy of concept processing capabilities based on the concept sciences. And again, when I'm talking about concept sciences, I'm talking about all the sciences that examine concepts, which again, for example, are psychology, linguistics, or the neurosciences. And this taxonomy of concept processing capabilities in the end is called the concepts lifecycle. And the third and the last step of my research is going to be about finding algorithmized versions of this concept processing capabilities in the AI literature and assessing them along the taxonomy that I have developed in point number 2. And this how it is achieved is also reflected in the following agenda, meaning the next sections that we are going to have a look at, respectively, the systems in focus and the nature of concepts will be about the theoretical part of the definitions that need to be clarified in order to understand the 4th chapter, namely the concepts lifecycle in AI systems. And in the end, I will provide you with some struggles that I currently have with the concepts lifecycle. And these struggles will be addressed in the uncertain paths forward chapter, respectively chapter number 5. And in the end, we will have a short look at the outlook. So let us start with the first content chapter of today, which is about the 2 systems in focus. And as I've already mentioned before, I would like to focus on HI systems, meaning human intelligence systems, and artificial intelligence systems. And again, the idea is to review the current HI systems literature, which is about concepts, and thereby derive a taxonomy, which is about concept processing in the end. And using these insights, these concept processing capabilities from the human intelligence systems research, and compare it with the already algorithmatized versions of these concept processing capabilities in the artificial intelligence systems research. And the two systems of interest, they have at least one commonality, which is this systems notion, meaning the two systems, they consist of a group of interacting or interrelated elements that act according to a set of rules to form a unified whole with emergent properties. But as you will see on the following slide, these elements, the set of rules, and the emerging properties, they differ significantly. So I have tried to illustrate what I mean with this. And as you can see on this slide here, I'm interested when I talk about HI systems, about our brain basically, which consists of billions of neurons and billions of connections in between neurons, the so-called synapses, which exchange biochemical and biophysical signals and thereby produce so-called emergent properties, such as our prediction capabilities and our behavior and all the conscious experience that we have. At least that is how I phrase the brain in the context of this research. And on the other hand, we have AI systems, and here is now illustrated a so-called deep learning net, which basically has implemented virtual neurons and virtual connections between the neurons that again form also according to a set of rules, emergent prediction capabilities and behavior. But although these things that I've just mentioned seem to be quite similar, they are not. There are fundamental difference between the two systems. It's just a mere complexity, which is much more difficult in brains than in AI systems. And we have many, many other things that are significantly different between the two systems of interest. It is very important that when I talk about AI systems, not only refer to so-called subsymbolic AI, which is basically neural nets, which have knowledge representations distributed along the neural net structures, but I also refer to so-called symbolic AI systems, which contain knowledge in terms of if-else conditions or in terms of rules that are integrated into the system itself. And again, I do think that, I mean, you can describe it as that these symbolic AI systems have this virtual if-else conditions as a foundation, and they can also have behavior and prediction capabilities which evolve from these symbolic representations of knowledge. So these are the two systems of interest that I want to have a closer look at in my research. And the next chapter is going to be about the nature of concepts. So I would like to start this next chapter with a quotation from Mitchell, Melanie Mitchell, who's a researcher in the AI realm. And she said that understanding what concepts are will be essential for engineering non-brittle AI systems. And I think that this is a pretty good point. I think we need to understand what these things, what we call concepts, are in opening not only the black box a little bit more or to shed light on the black box, but also to make the AI more powerful, more reliable, and maybe more responsible. And therefore, we need to get a better understanding of what these concept things are. And in philosophy of mind and in the neuroscience and in the linguistics and psychology, there are many different views that have different theories and definitions about what concepts are. And in the following, I will introduce you to the one that is especially interesting for the research endeavor that I am conducting. And for doing so, I have prepared the following slide. So in my research, concepts are considered as mental representations. And the mental attribute refers to the characteristics of representations of being integrated in cognitive systems. So I'm not talking about any representations, but about a very special kind of representations, which is integrated in cognitive systems. And the notion representation, that was how Hubbard, a philosopher, claimed, includes at least two kinds of worlds. On the one hand, a representing world, and on the other hand, a represented world. And the represented world, when we talk about AI systems or HI systems, is basically the real world that we as a system interact with. So meaning, or it could be also include like virtual worlds, but I consider virtual worlds as part of the real world. So for me, again, anything that we are interacting with on a daily basis can be considered as the represented world. And this represented world is somehow, again, represented in our representing world, which refers to the two cognitive systems of interest. And I've tried to illustrate how this could work on a very high level basis. So you can see here on the upper half of the graph on the human intelligence system side that we have on the right-hand side, sensory device, and we have our brain that interacts with the sensory device and tracks sensory data, which comes from the represented world, actually. And the sensory data devices could be, for example, our eyes, our ears, our nose, which again perceives some information about the represented world. It is important to mention here that our brain is not a blank sheet. On the contrary, it comes with concepts that are already being implemented, and the sensory data input, which comes from the represented world, is much interpreted before we receive it consciously. So there are processes going on that are related to the interpretation of the sensory data, which we are not aware of. But nonetheless, the idea is we perceive sensory data from the represented world, and the sensory data is represented in the physical structures of our brain. Meaning the idea is that the concepts that we perceive, which for example could be the object flower, has a sub-symbolic representations in the neurons and in the relations between the neurons. So this is like fundamentally, that's what I assume, the core of concept representation. That there are some struggles with this view I will talk later about, but again, this is how I phrase it in my paper. And on the other hand, we have artificial intelligence systems, and here these artificial intelligence systems also come with sensory data devices, for example, cameras or microphones or chemical detectors, which somehow simulate smell, even though they are in a very infant state as of right now. But we have sensory devices that again track the represented world, and the idea is that the representation of AI systems is not like happening in the hardware. I mean, it is, but it's not interpretable for humans, but it is embedded in like the virtual software logic that we have set up. And there we have, again, the two types of AI systems, the deep learning nets and the symbolic representations or the symbolic AIs. And whereas for the sub-symbolic representation part, we have the object flower distribute, or the concept of a flower distributed among the neurons and the connections between the neurons. And for symbolic AI, we have a system where the knowledge is already implemented within the system. So it's not really learned from the outside, but it could be assumed that you set up a symbolic AI algorithm that comes with a lot of if-else condition and thereby classifies ambiguous, complex data input from the represented world. But it is important to mention here that this sort of classification works not really well when it comes to symbolic AI algorithms. So because you need to, for every pixel combination, possibly have set up and if-else conditions that take care that this specific pixel combination is properly classified. And this is a rather hard task to do. So this concepts to be considered as mental representations view is not the only view that exists in the philosophy realm. In fact, there are many others, and in the following, I will introduce to you two other perspectives, which are valuable in specific contexts, but I have considered them as less pragmatic for my endeavor, and therefore I'm not applying this definition total, but I take aspects of it and consider them as even valuable for my endeavor here. So the very first view, which is often debated, is the concept as abstract objects view. And in this view, concepts are basically the meanings of words and phrases. And this view is specifically valuable when it comes to explaining concepts that are held by linguistic systems. But there are more systems that assumably hold representations than linguistic systems. And there are representations that are basically itself non-linguistic, even in linguistic systems. At least that's what psychology at the moment assumes. So I do think that this certain view is certainly valuable when it comes to examining representative or linguistic representations in linguistic systems, but it is not pragmatic for my current endeavor that also includes non-linguistic systems, respectively non-linguistic representations, such as many AI systems actually. One of these non-linguistic AI systems could be, for example, image recognition AIs, which do not need or do not use language, but rather merely focusing on the classification of incoming pixels and pictures. And there is another view which I consider as quite important when it comes to concepts, which is the concepts as abilities view. And hereby concepts are basically defined as an ability that the respective cognitive system has. And this is very important, this notion, since it acknowledges a so-called interpretative wiggle room of the current sciences that assume that concepts are in complex physical structures. What I do mean with this is that, for example, neuroscience, who is specialized on examining concepts and physical structures, often use so-called neural correlates to identify which physical structures are involved in which concept task. And this comes with a little issue because you always need to correlate the behavior of a system with its internal physical structures. And as of right now, we are not capable to describe the physical structures without having the behavior correlated. So just by looking at the physical structures, it is hard to create meaning for us humans. They are not interpretable for us as of right now. I mean, explainable AI is researching in how you can get meaning out of very complex connectivistic structures, but this is still ongoing research. And as of right now, it is not yet clear how to solve this black box problem or how to get rid of the interpretative wiggle room that exists in the neuroscience and in the deep learning community. And therefore, I think it is very important to have this in mind when I talk about concepts, that as of right now, concepts are always correlated with behavior. And but nevertheless, I do think that mental representations are somehow a more granular thing than abilities are. And therefore, I think in the end, if we gain more knowledge, hopefully mental representations are made for explaining abilities. So if you have an ability of a respective system, which is basically observed by looking at its behavior, and you want to explain this behavior, then you need to look into the internal states of the respective cognitive system, which again are partially the mental representations that its physical structures contain. So that is the assumption that I have when I talk about concepts. So this was a quick look at the philosophical debate. Again, this is not the main thing of my research, but I guess it is important to consider that there are other perspectives on concepts that are worth considering depending on the context. So that is it with the theory. And in the following chapter, I would like to talk about the main idea, the main framework of my research, which is the concepts life cycle in artificial intelligence systems. So what do I mean with the concepts life cycle? So for me, this concept life cycle describes how systems transform incorporated concepts during their life cycle. And when I talk about life cycle, then it refers to the concept part and not to the system part, meaning I would like to understand how concepts live in systems. And I would like to use this taxonomy, and you can see this in the purpose section, to structure the current HI research on concepts. And when I talk about HI research, I especially refer to the concept processing capabilities that have been examined in the human intelligence research. And based on this structured concept processing capabilities, I would like to assess the current AI capabilities that are there to transform concepts in the end. And as you can see here already, we have 4 phases along the concept's life cycle. And it starts with the innate phase, with the forming of new concepts, with the changing of concepts that are already existing in the system, and with the decay of, again, concepts that are already existing in the system of interest. I will go a little bit more into the details, what I do mean with these phases, but I think I will use this more illustrative slide here. And yeah, I will go from the left to the right. So I will introduce to you what I mean with the phases that I've outlined here. So starting with the innate phase. So the innate phase refers to the a priori integration of concepts into a system. And again, when I talk about system, I mean here about AI, I talk about AI systems or about HI systems. And these innate concepts are assumed by psychology at the moment. So psychology currently, or the empirical evidence there suggests, at least as it is interpreted by psychologists, that we come into this world with having already certain concepts being implemented into our brains. And these certain concepts are called primitives. So we come with primitive concepts into this world on which basis a more complex conceptual system is built. And we have, for example, primitives that concern fundamental understanding of space and time, that concern, for example, an understanding or a concept of agency, or that concern a concept of a causation, which we have already integrated when we come to this world. At least that is what developmental neuroscientists and psychologists currently assume. And the analogy for this a priori integration debate, you can also find their analogies in the artificial intelligence systems research, where developers or researchers debate of whether you should have implemented already some concepts into the AI systems. And one interesting notion here is, for example, the so-called hybrid AI systems, which combine symbolic and sub-symbolic approaches. And the idea is that in sub-symbolic or in symbolic, the symbolic parts represent already some very fundamental concepts that are being integrated, such as causation. So, or if certain conditions apply, then do this and this action. But nonetheless, this is still point of significant debate. There is one part of AI researchers which say, okay, we should come up with AI algorithms that are basically model free, or there is others who say we should come up with AI which is model based, meaning which already has some concepts being integrated into the algorithm itself. So this is the very first phase, meaning here I look at the state of the system before it comes to life, right? Or just from the start, when it is already there, what concepts are integrated there. And the next 3 phases, respectively, the form, the change, and the decay phase, they refer to the state after the system is alive and is like operating with or interacting with its real world, right? I mean, for the network, it is when it starts learning data. For the human, it is when it starts breathing outside the mother and when it starts interacting with the environment. Here with the formation phase, I mean the formation of new concepts within systems, and these new concepts can be formed by using either existing concepts from the conceptual system and by using data from the perceptual devices that we have, again, our eyes, our sounds that we listen to and on the smells and all the sensory data input that comes in. And the idea is that we use both of these components when we form new concepts. And this is also like the idea in the current research in psychology. Again, we are never a blank sheet, but we rather come with some concepts rudimentary being integrated into our system. And based on this very rudimentary conceptual system, we consequently enrich our conceptual system by meaningfully integrating data from our perceptual devices. So this is the form phase, and we also have the change phase, and this change phase refers to the change of concepts that are already exist in the system itself. And I have outlined here the changing of specific features. For example, features of a concept could be updated, they can be deleted, and then you have an original concept that is changed over time. It is important that when a certain feature is updated, it is not an essential feature, which is inherent part of the concept, but it is rather a feature that applies to a specific domain. And due to maybe an updated perceptual data input that says a specific feature is wrong, based on this basis, the feature is deleted. So this is what I do mean with change or with feature deletion here. It's not about the essential features, but rather about peripheral features. And then we have the decay phase, which refers to the structured forgetting of specific concepts in the system. So again, we think about a system that exists within the system and then is deleted over time. And this is summarized in the decay phase. And actually, forgetting is not as unstructured as we may think, but forgetting is a very well structured process where we structurally sort out information that are not relevant for our predictions that we do in order to act meaningful with our environment. So these are the 4 phases along which I want to organize the literature that I'm going to review. And I have started, and this now is a very work in progress state that I will show here. So I started to, again, map operations that I have identified in the concept sciences to these phases. And these operations, or this table, what you can see here, could be in the end the core of this research. So the idea, again, is to identify operations in the concept sciences and map them and organize them in meaningful ways. So here you can find, for example, in the innate phase, the primitives integrations. You can find other operations in the form and change part, for example, the generalization, abstraction, analogy making, specification, etc. And in the decay phase, you can find, for example, operations such as the proactive, retroactive interference, etc. I won't go into the details of the specific operations here. I think it would take too much time. And again, the idea is to find algorithmized versions of these operations in the concept sciences in the current AI literature. So I would like to somehow understand where are we in AI research when it comes to simulating operations that humans use to process concepts. And you can find these operations on the right-hand side. But again, it is a very early stage research here. So this table will hopefully be completed or will be complemented with other operations in the AI research soon. So again, this is more or less hopefully the core result of my paper, which is basically about understanding where we are in the AI research when it comes to concept processing in contrast to humans. So the next chapter will be about the thing, what I'm struggling now. And it actually will not be so much about the thing that I'm struggling, but it will be about an alternative view, which could be also interesting for research and where I'm actually thinking about rather going this path than the other, because the concept's life cycle is actually a quite broad topic, and there are many demarcation problems, such as how can I differentiate a concept from an operation in a physical system. I mean, as of right now, in the neuroscience, for example, concepts itself are considered as objects, or as processes, meaning concepts are fundamentally neurons that fire in a specific sequence. And same applies for the concept processing capabilities. They are itself also considered as processes, meaning as neurons that fire in a specific sequence and are interacting with the concepts that we are having implemented. So it is, from a neuroscience perspective, a quite hard thing to do to differentiate in a specific concept and in the physical structures that are involved in a specific concept processing. And therefore, yeah, we have this many demarcation problems. And it's not only that, by the way. Another issue is, how can I differentiate, for example, a concept processing capability from another general cognitive capability? And there it is also a rather blurred line. And I do not want to examine all cognitive capabilities, but only those who are transforming and processing concepts. But so far, it's rather hard to demarcate, in my opinion, at the moment. And therefore, again, I'm thinking about another research that I could potentially conduct, which is about the concepts format. And the concepts format is basically about the descriptions of the physical structures in which concepts are embedded, and also about the nature of these physical structures, what concepts supposed to be. And so let's think about, I'm not talking about, or talking in the following about the concepts life cycle, but about the concepts format in artificial intelligence systems. Then the result, or the things that I'm interested in, could look like the following. So in the end, I compare the concept structures of HI systems with the concept structures of AI systems. And there is actually a lot of literature that can be found in this regard, meaning, and I have two examples that I could still introduce here. I still have a little bit of time, but I won't focus here on everything, but only on the two that are, to me, very interesting, which is at very first the flexible versus stable characteristics, and second is the observability characteristics of concept structures. So let us have a quick look at the flexible nature of concepts in HI systems and in AI systems. So empirical evidence suggests that concepts are situational dependent mental entities. They are comprised of semantic features which are flexible recruited depending on the contextual constraints. That's how current neuroscientists and psychologists frame this flexible characteristics of human, or of representations of concepts being implemented in human intelligence systems. What does it mean? It means that depending on the situation we humans are in, the concept of one specific thing of the real world differs. And this example, for example, could be, if you as a human are asked in nature about what a bird is, then you're likely to retrieve features such as it can fly, it makes a certain sound in nature, it breathes, etc. And on the other hand, if you are, for example, in a restaurant, you tend to describe the bird concept with slightly other features, meaning for you, the bird feature is much more related to its eatable characteristics. So it's not so much living, but it could be more a chicken that tastes good, and that is maybe salty when you taste it in combination with the proper spices. But you have different associations and different features that you retrieve from your conceptual system, depending on the situation you're in. And this is also, again, backed up by neuroscience, which shows that different neural structures are involved that have different tasks or are responsible for different tasks, for example, object recognition or processing of more abstract concepts. And these structures, again, also depending on the specific task that you're confronting a subject with. So is it in nature or is it in a restaurant? Different structures in the brain are involved when it comes to the processing of object concepts. And in the AI research realm, we also have both parts of the scale represented. So when we look at the symbolic AI, we have a rather stable retrieval of concepts and of concepts features. And I have like shown here the so-called knowledge graph as an example. There you have like categories and subcategories organized and features that are assigned to categories. And the idea here is that you can think of specific situations where you retrieve different descriptions of a concept, meaning different features. But this retrieval is much more restricted because, again, you need to include for every single situation a certain if-else condition that represents a certain set of features. And this is quite hard to achieve. So therefore, I classified the structure as rather stable. It is potentially possible, but it's very hard to implement in the end. And when we look at AI systems, we have like a whole research area that focuses on so-called feature learning. And this research area basically looks at certain parts of a picture, for example, and tries to break this picture into little sub-pictures, and the sub-pictures itself represent certain features of an overall object. And within feature learning, it is possible to classify an object by only having a few features available. So if, for example, only the tire and only the steering instrument is visible in a picture, then the AI is still capable of classifying the respective object to a specific concept category. So we have these different sorts of concepts formats also being represented in the logics of a subsymbolic AI algorithm. And again, the idea is to elaborate, to dig a little bit deeper on these concept structures, depending on the respective system, and look for how these structures of AI systems are in the end being simulated in AI systems. So we only have 2 minutes, and that's why I'm going to skip the observability issue, and I'd rather focus on the outlook. So what I want to do next is the following. I would like to finalize the theoretical fundament of my research and thereby also decide on the way forward. I want to develop and refine my methodology. Again, I would like to apply a systematic literature review methodology, and therefore I need to come up with a proper base of keywords that I can use to query the scientific databases, and I need to play with these keywords and develop a solid fundament which is meaningful. And then in the end, for sure, I would like to conduct the literature review itself, and I want to hopefully create a paper that provides some value to the scientific community. All right, so that is it about my research. Thanks a lot for listening, and if you have any questions, then please feel free to ask.